Hello students, so in this session today now we are going to study about induction and inductor. Okay, in electromagnetic induction we have discussed a lot about the inducing current, inducing EMF, or about induction, then regarding the direction of induced EMF, regarding the direction of induced current, all these things we have discussed a lot. Now this property of electromagnetic induction, okay, this happens mainly in a coil. This happens in coils generally, a coil of single turn or a coil of many number of turns. So this property, when we utilize in a coil, and if we make it in advantage for us, that kind of device is called inductor. Just like resistance is a property, so resistance is opposing the current, so that resistivity property we have used and we made resistors. Okay, so same way this induction, electromagnetic induction, we make use of it and we make such devices which are called inductors. Okay, so this topic, okay, we will study in detail, okay, regarding inductor. So we will have to discuss about induction, how inductor behaves in electric circuits. All these things we will discuss today. Okay, so first we will discuss about induction. Okay, so induction is what? Induction is the property of a coil in which it opposes the growth and decay of current. Okay, so already in this chapter, right from the beginning, what we are studying, electric flux will be there. Change in electric flux will induce EMF in the circuit. So if EMF is there, then if it is a closed circuit, then there is going to be current, and this induced EMF, why it is induced there? In order to oppose the change which is happening there. Okay, so the direction of induced EMF is opposing the change. All these things we have discussed. Now the summary of all those things we will be utilizing here. Okay, this is what induction is: the property of a coil in which it opposes the growth and decay of current. Okay, growth and decay of current, okay, flowing through it flowing through it or in any coil near it. Okay, so induction is the property of a coil in which it opposes the growth and decay of current flowing through it or in any coil near it. Okay, so take down this definition, we will explain, we will discuss about this. Okay, now what they are saying, this induction is the property which opposes the growth and decay of the current in that coil or in the any other coil, any other neighboring coil. That is, in short, if we pass current through an inductor, okay, if we pass current through an inductor, okay, this current, suppose if this current is not constant, okay, suppose if this current is growing, okay, if this current is growing means this current value is increasing. So, one example is AC signal. alternating current. If IT, suppose if this is how the current is moving, current is growing, like the current is increasing, then current will decrease like that. This is variable current. Suppose if the current is like this, okay, 1 ampere, this is constant current. Okay, so any varying current, okay, so current can be varying also, current can be constant also, anything is possible. Suppose if you pass a varying current, suppose if this current is growing, this current is increasing, like 1 ampere, 2 ampere, it is changing, 3 ampere, 1.1 ampere, 1.2 ampere. From 1 to 2 ampere, when it changes, when it increases, in between 1.1, 1.2 also can come, right? So same way, if it is increasing, there will be an induced EMF and current in this coil. If it is a closed circuit, since it is a closed circuit, only current is coming. So if this happens, the EMF will be induced in this coil in such a way that which will oppose this current. This EMF is going to oppose this current. Same way, if there is a coil and current is flowing through this and this current value is decreasing, then EMF will be induced in this coil or current will be induced in this coil in such a way that it will try to increase this current. It will try to help this current to move. That is, inductor doesn't like changes. If current is increasing, it will oppose that increase. If current is decreasing, it will oppose that reduction in current. That is what we will discuss everything in detail. First you note it down. Okay, clear? Okay, so three situations are possible. First situation, a coil, okay, current is coming and this current is increasing. Second situation is a coil and current is passing through this is decreasing. Third situation is a coil and current is passing and this current is constant. Okay, this current is constant. Okay, so these three situations are there. If current is increasing, then the induced EMF will oppose, or this coil opposes the growth in current. Opposes the growth in current. So this will try to oppose that growth in current. Here current is decreasing, so it opposes the decay. So what will happen? This will try to compensate this reduction. If I is constant, no induced EMF. Current is constant, there will not be any induced EMF. Okay, clear? So from this, what I am going to tell you certain things is like, in this case, this induced EMF will oppose the current. Okay, so what will happen? If current is coming like this, EMF will be induced in this coil. Okay, EMF due to this inductor. Okay, okay, so that will be that EMF will be in such a direction that its positive terminal will come here, so that the induced current will be flowing in the opposite direction. So this is what is opposition. Correct or what? In this way, in this thing, what happens? In this thing, this current is coming, it opposes the decay. It opposes the decay, means this wants to help this, because this is going down. So what will be the direction of induced EMF? Current is coming in this direction and this current is decreasing. Here this current is increasing, so this wants to oppose. Here the current is decreasing, it wants to help, opposing the decay. So the induced EMF will be in this direction. Let us put this as VL. Okay, so the current induced in inductor, we generally name the voltage induced in inductor, we generally name it as L. Okay, L. Okay, this is L. Clear or what? So just like for resistance R and for capacitor C, for inductor we used to say L, not I, because I will be confused with the current. So general convention is to use L. Okay, so this is an inductor of value L, we can say like that. So this is how the circuit can be replaced like. Okay, so this VL direction will be in this way. Clear? And here no induced EMF. VL will be 0 since the current is constant. So what will happen? This will appear like a short circuit. This will appear like a short circuit. There won't be any resistance, simply the current will pass through this. Okay, so how to calculate the induced EMF, all these things we will discuss. Now just for an introduction I am telling you this. Clear? Please note it down. Okay, so induction can happen in two ways. Okay, one way is self-induction. One process is self-induction. Second process is mutual induction. Okay, so here this is nothing but formation of induced EMF and current due to its own current, due to its own change in current, there will be formation of induced EMF and current. Okay, so I will write here, this is formation, or we can say induction itself. Okay, induction happens, what? Induction of current, induction of EMF happens due to its own current, due to its own, let us be very precise and specific, due to its own change in current. Okay, example is, suppose if this is a coil, a current is passing through this coil and this current is either increasing or decreasing, then there will be an induced EMF, there will be an induced EMF VL, there will be an induced EMF VL. Okay, so due to the same current, that is what is self-induction. Okay, and self-induction we name as L. As I said before, self-induction we name this as L. Okay, self-induction L. Now what about mutual induction? Okay, please note it down. Pause the screen and note it down. Okay, what about mutual induction? We denote mutual induction as M. Okay, induction happens due to the change in current due to the change in current in the neighboring coil. Neighboring coil. Okay, so example I'll draw here. So this is a coil. Okay, so current is increasing or current is decreasing here. Okay, current. Now here there is another coil. Okay, so this is coil 1 and this is coil 2. Now due to the change in current here, there will be induced EMF here. So suppose if this is inductor 1 and this is inductor 2, then this will develop an induced EMF due to whom? Due to this. Due to C1. Okay, that is what is mutual induction. Just introduction. We will discuss the concepts in detail. Clear? Please note it down. Okay, so we will slowly move. This we will discuss later. One by one we will move step by step. First we will understand very clearly why this induction happens and all. Okay, how we should handle them. Everything we will discuss. Slowly we will move into the final concepts also. Okay. Okay, so what happens? Okay, like okay, so current flows here. When current changes, okay, when current flows through this, definitely what will happen? When current is there, magnetic field also will be there. When current is there, magnetic field also will be there. Okay, so when this current changes, okay, so this is the first criteria. When current changes, what will happen? Okay, this is the second thing that is going to happen. Magnetic field also changes. Okay, now we know when magnetic field is there, there is going to be magnetic flux. What is that? B dot A. So when flux is there, if the direction of magnetic field and direction of area, everything is same, okay, we can say BA. So if there are n number of turns, we say NBA. Okay, so what happens when magnetic field changes? Okay, any one changes, what will happen? This flux also will change. When flux changes, EMF will be there, because already we have studied E is equal to what? d phi by dt. So when current changes, magnetic field changes. When magnetic field changes, what happens? This flux, okay, this changes. When flux changes, it will lead to EMF, okay, induced EMF. So that is the reason when current increases, okay, when current increases or when current decreases, what will happen? Magnetic field increases, or if this is decreases, magnetic field decreases. when magnetic field increases, what will happen? This flux also will increase. When there is change in flux, EMF will be induced. When there is decrease in flux, EMF will be induced. Okay, whether flux increases or flux decreases, EMF will be induced, but the direction of EMF will be based on that. This is the primary reason for this induction. Okay, clear? Okay, fine. Okay, shall I raise? This is the primary reason for induction. Okay. Now, what will happen later when the current becomes constant? When current becomes constant, what will happen? There won't be any change in magnetic field, magnetic flux, and there won't be any induced EMF also. So, suppose if we consider a circuit, okay, so this is a switch. Now when the switch is open, that is when there is no current in the circuit, no EMF, no change in EMF, no change in flux, no change in current, no change in magnetic field, there won't be any EMF also. Now when I switch on, okay, when I switched it on, here current was 0, okay, initially current was 0, okay, this was switched off. Okay, I will step by step I will draw. This is inductor, battery, switch. So let this be the first circuit. Okay, so here current is 0, okay, so no induced EMF, nothing. Now when it is switched on, second circuit, initially current was 0, but now when current comes, so when current comes, what is happening here? Initially current was 0 at a time t is equal to 0. Now at a time t, okay, what happens? The current is increasing to I. Current is coming now. So immediately what will happen? Immediately this will try to oppose. So at that moment there will be an induced EMF which will try to oppose. So when current is coming in this direction, this induced EMF will be opposing this current. So the induced current will be in the opposite direction. This happens for a short duration of time. Because after opposing this current will start moving in this. Once if the current starts moving, okay, once the current starts moving, okay, now the current is moving here, current is moving in this, current reached here. Now once the current starts moving inside the inductor, this is DC source, that is, this supplies only constant current. So later what will happen? This will become a constant current. So when current becomes constant, induced EMF will become 0. Initially when current was 0, immediately when current came, it opposes. When the current starts moving, overcoming this opposition, finally when the current is keep on coming, no change in current now. So inductor doesn't have any problem here. So inductor will not oppose, VL will become 0. Clear? Pause the screen and note it down. So once the current is constant, then there is no induced EMF. I am telling you in terms of DC. When we connect a DC source, initially there will be an induced EMF which will oppose the current. Then once the current settles down in the circuit, then there will not be any induced EMF. This happens for a short duration of time. Okay, clear? Note it down. So once the current is constant, what will happen? This will be just like a short circuit. Now this current is settled, means after 1 second, okay, this opposition will be for very small time duration, maybe microsecond or millisecond or nanosecond. Millisecond is also maximum. Okay, at least after 1 second this will settle down. Clear? Please note it down. Okay, just we will do the comparison between resistance and inductor. Suppose if this is a DC source, this is a resistance. Okay, now this is current, this is time, Now suppose if this is E and this is R, this is EMF E and this is resistance R. What is the maximum current in the circuit? Maximum current means initially because of this resistance, initially this current will take a small time to develop. Anyway, you need not tell anything about maximum current, you will get confused. Just tell me what is the current here. The current which is going to be in this circuit is nothing but I is equal to E by R. Okay, now just see in this graph, this current will become E by R after a very short time duration. Initially, that is not even 1 second, very small time duration, maybe nanosecond. A short time duration it will take and it will reach E by R. That is the reason I said what is the maximum current, because in between 0 second and maybe 1 nanosecond this current will be developed, but we will not recognize it because it is of short duration. Now let us take a circuit with a coil. Now I have put here one coil. This is the circuit. So here one coil. So this is an inductor of 1 turn. Now how much time? This time it will take. Okay, so I could say it will take comparatively longer duration than this. Finally what will happen? This current also will be E by R. This current also will become E by R. So maybe at a time T dash, once it reaches T dash, what will happen? This will act like a short circuit. Okay, so after T dash, is it clear? Suppose if I put more number of coils, 1, 2, 3, 4, okay, I put some number of turns. When I added number of turns, what will happen? The flux also will increase. So the change in flux will be associatively increase. So EMF also will increase, means induced EMF or opposing EMF will increase. So what will happen? If you draw a graph, okay, how much time this has taken? Just see, this is going to be more compared to this. So this is, maybe I could say this is T double dash. So once it reaches T double dash, then this also will become what? Okay, after T double dash, this will act like a short circuit. Okay, so resistance also will create opposition, but we hardly notice it. One turn is there, okay, some time delay is there for current to become maximum. This is nothing but the maximum current. This is maximum current. Now here this is the maximum current. Now this reaches E by R. This is also what? E by R. Okay. So here suppose if we put a resistance here, we will put a resistance here, R. We need to put a resistance here, R. So we can say that the maximum current is E by R. Clear? Please note it down. Okay, now we will see more details about induction or that coefficient of inductance. We will see in details and we will get into the formula and other things. Okay, so whatever we have discussed, we will quickly recap it. Inductance is the opposition to the growth or decay of current. Okay, induction is the opposition to either growth or decay of the current. There are two types of induction. One is self-induction, another is mutual induction. Self-induction is the opposition due to the current in on coil. I mean the opposition by the coil because of its own growth or decay of current. Whatever we have discussed in the previous examples. Okay, see, if this is a coil, now current is here. In this case, self-induction. Okay, mutual induction. So because of this current, there is going to be an EMF in the opposite direction. Okay, if this current is increasing, if this current is decreasing, then an EMF will be generated here in order to oppose this reduction in the coil. Then we said if it is just a resistance, then in the graph it will take a small delay in order to achieve the maximum current. Okay, then suppose if there is two coils, then it will take a little bit more time. If there is so many coils, then there will be a little bit more delay. Likewise, so all these things we have discussed in this is actually self-induction. Mutual induction is what? If this is one coil, let it be there, this is another coil. Now here the current in this coil is increasing or current in this coil is decreasing. So there will be EMF, induced EMF in the another coil. Need not be connected also. There is no necessity for connection also, but EMF will be induced in the other coil. Suppose if this is solenoid, okay, this is a solenoid. We wound another piece of wire like this. Current is passed in this, then there will be induced EMF in the other one. That is what is mutual induction. So this is the difference between self-induction and mutual induction. Now we will discuss the details of induction. Okay. Pause the screen and note it down. Okay. So generally induction depends on induction depends on number one, shape and size of the loop. Shape and size of loop. Okay, shape and size of the loop. Number two, number of turns. Number of turns. Number 3, the medium in which it is, the medium in which it is wounded. Say for example, if we use iron core, if this is iron and we are winding, making the winding like this, okay, then this area of this, shape of this, number of turns, at the same time this material, okay, all these will decide the induction. Okay, induction. So the inductance, okay, we can say inductance depends on all these factors. Unit is Henry. Unit is Henry. Clear? Okay. Note it down, please note it down. Okay, so first we will discuss details about self-induction. Okay, so self-induction. Okay, self-induction. So first thing what we can say is flux. Flux through a coil. Flux through a coil is directly proportional to the current passing through it. Before, previously we have seen like flux is equal to B dot A, or phi is equal to what, N into B dot A. This we have seen already, okay, in the beginning of electromagnetic induction. Here we are going to see in another angle, because if current is there, definitely magnetic field will be there. If current is there, definitely magnetic field will be there. Correct or what? So here phi is proportional to I. Now when we equate this, the constant will come. That constant is what is inductance. Okay, so this is what is inductance. Okay, now if there are n turns, then n phi is equal to Li. So this is what is, remember this relation, phi is equal to Li, n phi is equal to Li. This is what is inductance. Clear? So what is induced EMF? What is induced EMF? Induced EMF is equal to minus d phi by dt. So here E is equal to minus what we can write, L d Li by dt. E is equal to minus L d Li by dt. So here this is constant. This is constant for a particular solenoid, or for a particular inductor, or this is constant for a particular number of turns. When you take an inductor, inductance will be constant. So we can say E is equal to minus L di by dt, minus L di by dt. So sometimes we can even write in this way also, minus L delta I by delta t, also interchangeably we can use. Please note it down. Okay, clear? Now n phi, if there are phi number of turns, then suppose E is equal to, if n number of turns are there, minus d by dt of n phi, we can write like that, n phi. Okay, so still what, E is equal to minus d by dt of Li. So in short, we can say EMF is equal to minus L di by dt. Okay, remember this relation. This is also important, this is also important regarding self-induction. Now we will see self-inductance of a solenoid. Self-inductance of a solenoid. Okay, self-inductance of a solenoid. So why we are so particular about self-inductance of a solenoid? Why? Because an inductor, okay, this is used as a device, okay, just like a resistance. So if we consider an inductor, the inductor will be just like this. A soft iron core will be there. On that there will be windings. Okay, so and this will be used as inductor. Okay, so inductor is a device. Okay, so you know that. So because this inductor, the inductor which is used as a device, this is actually what? Solenoid or soft iron core, and on that so many windings will be made, which is nothing but solenoid. Okay, so self-inductance of a solenoid. What is a solenoid? If this is a soft iron core, okay, we will be making okay, so this is a soft iron core. Its length is L and this radius is R. We can assume that this L length is very much greater than this radius R. This is very long solenoid. Current I is passing through this. The area of cross section of this is A. So this is the solenoid which we are considering. Clear? Now first thing is magnetic field. Okay, now what we are going to find? Okay, we are going to find the self-inductance of the solenoid. So first thing is we know N phi is equal to what? Li. N phi is equal to Li. Why N phi? Because so many number of turns are there. N phi is equal to Li. So from that, this L, the formula for L can be found. Okay, so what is the self-inductance of a solenoid? We can find from this. Okay, so what is phi? Phi is actually B dot A. If the magnetic field is going like this and if the area is like this, okay, if this is the area vector, this is area vector, and the magnetic field is also going like this, then we can say phi is equal to BA for n turns. When there are n turns, then what? Phi is equal to NBA. NBA. Okay, now what we can write is, what is a magnetic field due to solenoid? Magnetic field inside solenoid is what? B is equal to what? B is equal to, we have assumed that this length is very much greater than the radius. So for that case we have already mu 0 Ni. Mu 0 Ni. This is the magnetic field due to a solenoid. Now what is this N? This N is number of turns per unit length, number of turns per unit length. So what is this n? Number of turns per unit length means total number of turns divided by L. So this magnetic field B is going to be mu 0 Ni divided by L, we can say. Mu 0 Ni divided by L. Clear? Okay. Now shall I erase this? Okay. So magnetic flux is what? Magnetic flux is magnetic flux in a single coil into the number of turns. Okay, magnetic flux, total magnetic flux will be what? Magnetic flux through a single coil. Okay, single coil into the number of turns. Okay, so here already we got B is equal to mu 0 Ni. Okay, B is mu 0 Ni. Now using this we can say that B is equal, flux is equal to B dot A or NBA, total flux. Okay, so this is equal to N into mu 0 Ni into A, or we can say N into mu 0 N by L, okay, into A. So this is mu 0 N square mu 0 N square I A divided by L. Okay, fine. Okay, length. Okay, so phi is equal to mu 0 N square I A divided by length. Length we will put this as small letter. Length. Clear or what? So this is phi. So phi is equal to what? Mu 0 N square IA divided by its length. Correct or what? Now already we have studied phi is equal to, okay, phi is equal to this also we have seen. Total flux is equal to N into the flux through a single coil. This is equal to Li we have seen. Li we have seen. Now this formula we can put here. Mu 0 N square IA divided by L. This we can write here. So comparing these two, this I and I is here. From that I could say that self inductance L is equal to mu 0 N square A divided by L. So this is the formula for inductance of a solenoid. Okay, please note it down. Okay, this is the formula for inductance of a solenoid. Okay, clear? Pause the screen and note it down. Okay, so the same solenoid, okay, in electric circuits we call them inductor. Clear? Please note it down. Okay, clear? Shall I erase this? We will analyze this formula a little bit. Okay, so L is equal to mu 0 N square A divided by L. Now we can say that L is directly proportional to A. okay, area. So inductance is directly proportional to area. So based on the area, if it is circular, it will have some inductance. If it is square, it will have some other inductance. Okay, so area, so we can say that this comprises size and shape. Size and shape, point number 1. Another is what? Point number 2. L is proportional to, inversely proportional to the length. So here also size comes. Third point, L is directly proportional to n square. This n, small n has difference. Small n is what? N by L, total number of turns by L, that is number of turns per unit length. This is total number of turns. Okay, so total turns. Okay, so this you must remember. Another thing is what? Mu naught. Fourth point is L is proportional to mu naught. When I say this is actually material. This is actually material. So instead of mu naught, I would say mu. What is this mu? Mu is mu naught into mu r. This mu r is relative permeability. Okay, so mu r, okay, different for iron. Okay, say if we take steel, okay, if we take steel, or okay, for air, okay, for them this is different. Okay, so we can finally say L is equal to mu naught mu r n square a divided by L. Okay, this is also possible. Clear? Please note it down. Clear? Next one is energy stored in an inductor. Energy stored in an inductor. Okay, energy stored in an inductor. So energy will be stored in capacitor. Okay, you might have studied already. Energy stored in a capacitor is in the form of what? Electrical energy. Okay, so here in inductor, energy will be stored as a magnetic energy. Okay, so here suppose if we consider an inductor, this is a battery and a switch. So this is the EMF here. Okay, this is a switch. Okay, this is the inductor. Now suppose when we switch it on, definitely there is going to be a resistance here. Okay, so when we switch it on, there will be an induced EMF. So what will be that induced EMF? So VL is going to be what? VL is going to be L di by dt. Correct or what? Already we have seen the minus will come, minus will be there, but we are concentrating only on the magnitude. We are going to find energy. So VL is equal to L di by dt. Immediately when it is switched on, what will happen? Immediately when it is switched on, it was zero current. Okay, at a time t is equal to 0, I was 0. At a time t is equal to t dash, okay, I is started coming. So immediate change, this will oppose. So there will be an induced EMF in order to oppose that. That is what L into di by dt. Now, what is I? What is I? I is equal to dq by dt. Okay, so can we write VL is equal to let it be there. Okay, let it be there. Before that, there is a concept or there is a definition for EMF. What is that EMF? EMF is the work done per unit charge. Work done per unit charge. That also we know. We need to consider that. Another point is when this EMF opposes the current, still what happens? After some time, after a small duration of time, current will pass through this. So overcoming an opposition, for the current to pass through the inductor, a work will have to be done. So we can say that, okay, for current to pass through the inductor, work will have to be done. Okay, and this work will be stored as energy. This work will be stored as energy. Okay, this work will be stored as energy. Clear or what? Okay. Okay, so we know what is EMF. The definition of EMF is equal to work done per unit charge. That is, EMF is actually, one definition of EMF is, we have discussed this in current electricity also. The definition for EMF is work done, okay, in order to take the unit charge through that closed circuit. So this is work done in order to move that unit charge, okay, work done in order to take the charge through that closed circuit. Okay, so work done per unit charge. Okay, so here, to do a small work, okay, we will have to do the work. So to do a small work, this is nothing but EMF into what? dq. EMF into dq. Now to do total work, we will have to do sum of all the small works. Okay, so this is equal to integral E dq. Okay, now what is E? Okay, if you have copied this, shall I erase this? Please copy till this. Pause the screen and note it down. Okay, shall I erase this now? Okay, so this E will be dropped here. So we can say that this E is nothing but VL, and this is same as L di by dt. Okay, the same EMF will be dropped here also. So what? W is equal to integral, we can say L di by dt into dq. Okay, now dq is what? I is equal to dq by dt. So for dq we can say I dt. So substituting that, work done will be what? Integral L di by dt into dq is I dt. So this dt can be cancelled off. Finally, work done will be what? Integral L I di. So we will put the limit. Current was 0. Initially current was 0. It will not allow to pass through it. Fine. After that, it will allow a little bit current. Finally, it will allow full current. So the work will have to be done in order to make the current in the inductor from 0 to I. It will not allow first. Then it will allow a little bit current. Then finally full current will be allowed. For that to happen, work will have to be done. So work done for 0 current, work done for 0.1. So work done for 0.1, work done for 0.2, work done till full current is passed. Full current will be passed. Okay, so 0 to what? 0 to I. 0 to I. Okay, 0 to I. So work done will be what? W is equal to L is constant. Now variable is actually I. So I square by 2, putting the limit 0 to I. So finally work done is nothing but half Li square. So this is nothing but the energy stored. This is nothing but the energy stored. Clear? Note it down. So energy stored in the inductor. Okay, please pause the screen and note it down. Okay, shall I erase this? Okay, so energy stored in an inductor. So work is done. That work will be stored as energy in the inductor. Energy stored will be what? Potential energy. So energy stored in the inductor, U is equal to half Li square. Half Li square. Clear? Next is energy density. Energy density. So energy density in the inductor. Energy density in the inductor. What is energy density? We know density is equal to what? Mass by volume we write, right? So generally energy density means energy per unit volume. Okay, so generally we say density is equal to mass by volume. Just to remember, to make us remember the concept, I am telling this. Mass by volume. Density is mass by volume. Energy density is energy by volume. So when we divide with the volume, we will be getting energy density. Okay, so energy density is equal to energy density small u. Okay, small u is equal to capital U by volume. What is capital U? Half Li square divided by volume. Okay, so U is equal to half into. So what was L? L is equal to mu 0 n square A divided by L. So that we will substitute here. This is equal to mu 0 n square A divided by L. This is divided by volume is what? Area into length. Volume is equal to what? Area into length. Okay, so this is, if we consider this is just like this is numerator, denominator, numerator, denominator. So energy density is equal to what will happen? This area this area will be cancelled off. Okay, so half into mu 0 n square divided by L square. Clear? Mu 0 n square divided by L square. Now we know magnetic field inside the inductor or solenoid is mu 0 Ni or mu 0 Ni divided by L. Okay, so here there is no I. Okay, okay, I is there, half, yeah, here I square, correct. So I missed I square here, students, please. So here again I square is there. So if we multiply this with the mu naught and divide with the mu naught, okay, we will be getting U is equal to, so mu 0 square n square I square. So that is what is B. Then L square is there. Okay, so we can say this is nothing but magnetic field square, okay, divide by 2 mu naught. Okay, so this is another expression for energy density. So okay, energy density, remember this also, and general formula is energy by volume. Clear? Please note it down. Energy density. Okay. Clear? Okay, so another important point is this doesn't allow any change, right? So this is just like inertia in our mechanics. Inertia doesn't allow to change the direction immediately. The inertia doesn't allow to move immediately. Inertia doesn't allow to stop immediately. Okay, all these effects will be there. So this is the inertia in electricity. Okay, electrical inertia is what is inductor. Okay, so inductor or inductance is inertia in electric circuits. Okay, remember this point also. Okay, okay, so we will summarize. Phi is equal to Li, or we can say if there are n number of turns, n phi is equal to Li. Then what is the voltage induced EMF in inductor? This is equal to minus L di by dt. Then fourth point is what is the value of inductance? Okay, mu 0 n square A divided by L. We can say this is in solenoid or inductor. Fifth point is what is the energy stored in inductor? Half Li square. Sixth point is energy density. Energy density is energy per unit volume. This is nothing but B square divided by 2 mu naught. Seventh point, just as in electric circuits, what will happen if in an inductor, okay, if current is increasing, then this circuit will act like after there will be VL, no, there will be voltage developed here, that VL will be there, but polarity will be opposing. Okay, suppose in the inductor if I is decreasing, then again what will happen, VL will be developed here, but here this will try to oppose this reduction, so polarity will be aiding the current. Okay, so this is all about self induction. Okay, self induction. Now we have to do problems on all these that we have to do, then only we will become comfortable with this, then we will have to study mutual induction also. Okay, hope you understood. Okay students, so thank you so much. We will see in another session. Bye bye.